So for our learning problem, our goal was to make a network that learns to generate letters and numbers that can be used as CAPTCHA codes. So ideally, the generated images would be legible for humans, but hard to classify for a machine. So similar to the pictures shown below. So a quick overview of how we did it. We made a GAN model for generating both a picture of a letter as well as a picture of a number, and we used the exact same model architecture for both problems, but we trained it on different subsets of the MNIST data set. So one of them we used the letters and the other we used numbers. And then we deployed both models to TensorFlow.js to create an interactive CAPTCHA generator. So the front end generated 3 random letters, 3 random numbers, and then it put it together to make a code. I'll show you a demo now.
For this project, we used a generative adversarial network, abbreviated as GAN, to generate characters that look vague to humans, but are extremely difficult for machines to identify. With GANs, you have 2 machine learning models, one called the generator and the other called the discriminator. The generator takes in a seed value, usually a vector of randomly generated numbers from a normal distribution, and generates an output of the shape of the data we are trying to generate. The discriminator's job is to discriminate between our real training data and the fake data generated by our generator. The discriminator takes an input of the shape of our data and outputs a single value between 0 and 1. We then use binary cross-entropy to calculate separate losses for both models. The generator's loss is taken as the proportion of generated data that the discriminator correctly identified, while the discriminator's loss is taken as the proportion of all data it incorrectly classified. We used a specific type of GAN for our project called the Deep Convolutional Generative Adversarial Network, or DC-GAN, which is particularly useful for generating images. With DC GANs, the generator is made up of a dense layer followed by multiple 2D convolution transpose layers that use strides to scale up the height and width of the input, while each consecutive layer uses fewer kernels than the last. The discriminator then works in reverse, using multiple 2D convolution layers with strides followed by a dense layer to scale down the input into a single value output with 10H activation.
So for our architecture, a lot of it is based on the DCGAN model, which was mentioned in the previous slide. We just optimized it to fit our data set, which was 28 by 28 by 1, as opposed to the 64 by 64 by 3 color image that was produced by the original one. Some things to note about our model. We have our generator and our discriminator, which are 2 separate models, but they have a lot of things in common. So one of those things is that we avoided using connected and dense layers, except for either in the input or the output, since those are known to not be good with generative networks. We use batch normalization layer after almost every single layer to standardize the input coming into the layer and make it train faster. We also use dropout layers after each convolution to avoid overfitting. For the optimizer for both of them, we used a atom optimizer, and we used cross-entropy for the loss function. In the generator, we used a convolution transpose layer with a stride so that we could upsample features, and that's pretty much similar to a regular convolution 2D layer, except it does the opposite. For the activation functions, we use ReLU activation functions for all the layers except for the very last one. We use 10H because our data was represented from -1 to 1 in terms of pixels, so 10H fit that the best.